All right, welcome everybody. Happy Monday morning. Any questions I can answer for you over log and exponential functions? Yes, sir. 85. Okay, so we want to find the derivative of 1 plus 1 over x to the x. Okay, so we have f of x is 1 plus 1 over x to the x. And so this is a perfect use of logarithmic differentiation. So I could say that, let's just call it y equals 1 plus 1 over x to the x. And so ln of y is equal to ln of 1 plus 1 over x to the x. But one of the properties of natural log is I could pull that exponent out in front. So I could write this as ln of y is equal to x times ln of 1 plus 1 over x. And now I could probably take the derivative of this equation using using implicit differentiation. And then, let's try that first and see how that goes. So the derivative of ln of y should be 1 over y times the derivative of y. That's the derivative of ln of y. And then over here we have a product. So we can use the product rule and I get the first x times the derivative of the natural log of 1 plus 1 over x. Okay. So the derivative of 1 plus 1 times ln of something. So I have ln of something. The derivative of ln of something is 1 over that thing times the derivative of that thing. So I get 1 over whatever's inside, 1 plus 1 over x, times the derivative of what's inside. The derivative of 1 is 0. The derivative of 1 over x, let's see, that's x to the negative 1. So the derivative of x to the negative 1 is negative x to the negative 2, or negative 1 over x squared. Okay, so we've got the first x times the derivative of the second plus the second, which is ln of 1 plus 1 over x, times the derivative of the first, which is just 1. Okay, so we've got all of this. Now we can multiply both sides by y, right? And y, we know what that is. It's this guy. So what I could do is I could say 1 over y times dy dx is equal to, I could simplify this a little bit. I have an x here and an x squared on bottom. So one of the x's cancels, and I'm just left with x. I could even multiply this x through here if I wanted to make it even more pretty, and I have negative 1 over, if I multiply x through, this is an x, and this is a 1. So I just get negative 1 over x plus 1, plus ln of 1 plus 1 over x. Now I can multiply both sides by y, and I get that dy over dx is equal to y times all of this stuff, right? Minus 1 over x plus 1 plus ln of 1 plus 1 over x. And then I can replace y by what I know it is in terms of x. So I know that y is 1 plus 1 over x to the x. So I could replace, and I get dy over dx is equal to 1 plus 1 over x to the x times all this other stuff. So negative 1 over x plus 1 plus ln of 1 plus 1 over x and close the parentheses. And so that's my derivative function.
So I did it like a little bit different way because you showed us like the e to the ln way.
Oh, yeah, that also works.
Okay, and then my answer was pretty much the same except for the first term was e to the x times ln. It was like e.
This
Yeah.
was a little different. What did you get?
E raised to the power of x ln of 1 plus 1 over x.
Oh, yeah.
Is that the same?
It is, because so this x can be moved up to the power, and then e to the ln of something is just that thing.
Okay.
So it's exactly the same.
Okay.
Yeah. Yes. Good question. This was 85. Yeah, so the way I did it certainly works the way you just suggested. It's actually doing the same thing. Instead of like, I'm taking ln of both sides and then using implicit differentiation, what you suggested doing is starting out by basically writing the function like this, right? And then you're taking the derivative of e to a power, which basically gives you the same derivative. So yeah, either way works. Other questions? Yeah.
If you have like ln and then you have the parentheses in the two terms,
Yes.
this would be different.
Not exactly. Which one are you thinking of?
25.
25. You can't just straight up distribute 25.
Oh, would that be the same thing we did in 85 and use the implicit differentiation?
For which one? I'm sorry. 25? 25, you don't have to do that at all. But I can do 25 really quick. Let's see. X squared plus 1 ln x. Is that right? X squared plus 1 ln x. Okay. So on this one, is this the one you were referring to? Yeah. This one, you don't have to do something quite as complicated as the last one. The reason that this one was a problem is because we have x's kind of in the base and x's in the exponent. So you have to do something to get that x out of the exponent. Here, you don't have any x's in the exponent, you just have a product. So we could just use the product rule to find the derivative. So we get dy dx is equal to the first times the derivative of just ln of x is just 1 over x plus the second ln x times the derivative of the first, which is 2x, and that's it. So you don't have to do, so not every time that you have an ln do you have to get fancy, so to speak. So if it's just ln of something and you know the derivative of that thing, then it's always just going to be 1 over whatever's right here. In this case, 1 over x times the derivative of what's right here. And in this case, it's not very interesting. That's just 1. So this is the derivative of ln x is just the 1 over x. Other questions? Yeah.
Can we do 73?
73, sure. Okay, 73. So 73, we have f of x equals ln of 2x minus 1 times x plus 2 cubed divided by 1 minus 4x squared. Okay, and this one they're asking you to calculate the derivative. Sometimes it's useful to use properties of logarithms to simplify first. Yeah, and I think that this is one of those cases where you probably want to simplify this a little bit first. And the way that you can do that is if you have ln of a product, of a quotient, then it's going to be the natural log of what's on top minus the natural log of what's on the bottom, right? So this could be written as ln of the top, which is 2x minus 1 times x plus 2 quantity cubed minus ln of what's on the bottom, which is 1 minus 4x squared. Now we have ln of a product, but ln of a product could be written as ln of the first thing plus ln of the second thing. So I could write this as f of x is equal to ln of 2x minus 1 plus ln of x plus 2 cubed minus ln of 1 minus 4x squared. And I could even go one step further before I even start taking the derivative, and that is that these powers could drop down in front of the ln. So I could take the 3 out in front of the ln, I could take the 2 out in front of the ln. If I did, I get f of x is equal to ln 2x minus 1 plus 3 ln of x plus 2 minus 2 ln of 1 minus 4x. Okay. So now I'm ready to take the derivative. So f prime of x is equal to the derivative of ln of something is 1 over that thing times the derivative of that thing. So it's 1 over 2x minus 1. And then I could just put the derivative of this on the top, which is just 2. So it's the derivative of the thing divided by 2x minus 1. Okay, same thing here. I have 3, but the 3 doesn't really do anything. It just stays there. And then the derivative of ln of x plus 2 is 1 over x plus 2 times the derivative of x plus 2, which is just 1. Okay, minus 2 times the derivative of ln of 1 minus 4x is 1 over 1 minus 4x times the derivative of 1 minus 4x, which is minus 4. So if we wanted to write that one more time, we have f prime of x is 2 over 2x minus 1 plus 3 over x plus 2 plus 8 over 1 minus 4x. That's it. Yeah.
Could you do 81?
81, sure. Okay, so 81, sort of similar. So 81, we have f of x is equal to x plus 1, 3 over 2, times x minus 4 to the 5/2. And then divided by 5x plus 3 to the 2/3. Okay, so this one doesn't actually have any ln's, right? But we might want to get some ln's involved. So the way that we could do this is one of two ways. Either the way that you suggested is that we make this e to the ln of that thing. That's one way to go. The other way is that we could like take the natural log of both sides of the equation. Either way is fine. Okay, they're actually the same process. So since writing e to all of this stuff sounds kind of horrible, I'll just take the natural log of both sides. So I'm just going to call this side y and say ln of y is equal to ln of all of that stuff. So this is x plus 1 to the 3/2 times x minus 4 to the 5/2 divided by 5x plus 3 to the 2/3. And the reason that I would even want to do such a thing is because now I can break all of this up like I did over here. So if I have ln of a quotient and a product, I can break it up into a lot of different small ln statements that are easy to take the derivative of, where right now this thing's kind of a mess. Okay, so let's break it up. So I still have ln of y is equal to, so if I break this up, I get ln of this one plus ln of this one minus ln of this one. So I have ln of x plus 1 to the 3/2 plus ln of x minus 4 to the 5/2. And then because this one's divided, I have minus ln of 5x plus 3 to the 2/3. Now by the power rule for logarithms, I can bring the exponents down in front of the ln. So I have ln of y is equal to, this is 3/2 ln of x plus 1 plus 5/2 ln x minus 4 minus 2/3 ln of 5x plus 3. And now we're finally ready to take a derivative. So I got this into a form that I like. So now taking the derivatives of each side, so I'm using implicit differentiation. The derivative of ln of y is 1 over y times dy dx. On this side, the derivative of 3/2 ln of something is 3/2 times, what's the derivative of ln of x plus 1?
1 over x. 1 over x.
1 over x plus 1. That's right. So it's 1 over whatever's sitting here. And then you ultimately, so it's 1 over x plus 1. And then ultimately it's times the derivative of x plus 1, but that's just 1. Okay. And then I get plus 5/2 times the derivative of ln of x minus 4. So what's the derivative of ln of x minus 4?
1 over x.
Yeah, 1 over x minus 4 times 1, I suppose. So it's times 1 over x minus 4. And then I have minus 2/3, that just stays. And then I have the derivative of ln of 5x plus 3, which is 1 over 5x plus 3. And do I need anything else? Times 5. Yeah, because the derivative of 5x plus 3 is 5, so I need times 5. Okay. I'm almost done. I'm trying to find dy dx, but I have this y sitting here. So if I multiplied both sides by y, I would be done, right? So I could write this as dy over dx is equal to y times all of this stuff. So I have 3 over 2 times 1 over x plus 1 plus 5 halves times 1 over x minus 4 minus, I could multiply that 5 by that 2 and get 10 thirds times 1 over 5x plus 3. And now I just plug back in for y. I know that y is what? Y, well, it's nasty, right? It's all of that. So I need to plug that back in for y. So when I do, I get that dy over dx is equal to y, which is this original function, which is x plus 1 to the 3 over 2 times x minus 4 to the 5 halves divided by 5x plus 3 to the 2 thirds times all of this other stuff. So 3 over 2 times 1 over x plus 1 plus 5 over 2 times 1 over x minus 4 minus 10 thirds times 1 over 5x plus 3. So that's pretty nasty, but that is the answer. So these look really bad at the end, but actually the process isn't that bad if you realize, oh, if I just take the natural log of both sides, I can turn this into something that really isn't that hard to take the derivative of. The answer looks terrible, but it wasn't actually that terrible to get there. Questions? Yeah.
Okay, so I'm comparing 73 and 81.
Yes.
So in 73, right, when you split it up,
Yep.
for the top two values, you multiplied them, and then in 83, you added them. Why did you do
Yep. Okay. Very good. So what I did is I took an intermediate step just to try to make sure everybody understood what I was doing in this stage. And that is that first I'm splitting them up as a quotient. So it's ln of the top minus ln of the bottom. So I did that. And then I said, but look, this itself is a product. So that's ln of the first plus ln of the second. And so then I wrote it like this. Over here, I skipped the middle step, and maybe that wasn't so good. But all I did is I say, okay, I've got ln of something times something divided by something. So that's ln of this one plus ln of this one minus ln of this one, which is exactly what I did here. I could have just gone from this step to this step without doing this middle step. I just did this middle step to make sure that everybody kind of knew what I was doing. And then over here, I skipped it, and maybe that wasn't so good, but does that make sense?
Yeah.
Yeah, so if you have like, even if I had like something times something times something on the top, and then something times something times something on the bottom, you could skip all the in-between steps and just say, and it was ln, of course. Then you'd have ln of the first one plus the second one plus the third one minus this one minus this one minus this one. Does that make sense? Yeah, so another way of thinking about it is you could move all the ones that are on the bottom to the top, but then they have negative exponents. So when those exponents come down, it will make it negative. So maybe that's too much, but yeah, that's why it's negative, is because the exponents on those things are negative. Yes. 65? Sure. Okay. So number 65. we have y equals cosine of ln of cosine squared of x. Cosine x times ln of cosine squared of x. Was this 65, did you say? Y equals cosine x times ln of cosine squared of x. That seem right? 65. Cosine x ln of cosine squared of x. Okay, very good. Okay, so want to take this derivative. The first thing that I see here is that it is the product of two things. So I need to use the product rule. Okay. So I take the derivative, dy dx, and I get the first one, leave it alone, cosine x, times the derivative of the second one. Now this is the one that's more interesting, right? So the derivative of ln of something is 1 over that thing times the derivative of that thing. So I could put the derivative of cosine squared of x on the top if I wanted to. So what is the derivative of cosine squared of x? Well, I suppose that's a chain rule problem. So the last thing that happens is the square. So the derivative of cosine of x squared is 2 cosine x, 2 cosine of x to the first, times the derivative of cosine of x, which is negative sine x. So that's the first times the derivative of the second. Are you with me? So far, so good. Any questions on that?
Why is it on the top?
Why is this cosine squared of x on the bottom?
That 2 cosine times.
Oh, why is this this one's on the top? Why is that there? Yeah. Remember, so just generally, if I'm trying to take the derivative of ln of any function f of x, okay, so I've got ln and then some x stuff here, right? Then the derivative is the derivative. Okay, so let's say that y equals that, then dy dx is equal to the derivative of that x stuff over that x stuff. Okay, so it doesn't matter what this is. You put that on the bottom, and then you put its derivative on the top. So that's what I did here, is I said, I need to take the derivative of ln of some stuff. So what do? I take whatever's right there, put it on the bottom. I take the derivative of this thing and put it on the top. And that's it. Yeah.
Wouldn't it be negative sine of x is in parentheses?
Negative sine of x
No, in the front of it.
here?
Yeah.
No, because what I'm doing, I'm not done yet, by the
Oh,
way.
okay, sorry.
Because what I'm doing, remember, first of all, I'm doing the product rule. And the product rule says, take the first one, leave it alone, multiply by the derivative of the second one, plus the second one, which is ln of cosine squared x, times the derivative of the first one, and the derivative of cosine of x is minus sine x. So that's the derivative. We could maybe make it look a little cleaner by canceling. Let's see, actually, we could make it a lot cleaner, right? Because there's a cosine here, and a cosine on bottom, a cosine here, and a cosine on the bottom. So those all cancel. And so we could definitely clean this up a little bit. This is minus 2 sine x plus, no, minus, I guess, minus sine x times ln of cosine squared of x. It's probably the best we can do if we were simplifying. Does that make sense now? Why I had the cosine here? Yeah, it was just leaving that first piece of the product alone. Yeah,
71.
71. Let's take a look. So 71, okay. We have ln of the square root of 10x. Okay, ln square root. So 71. We have y equals ln square root of 10x. Okay, so this one I just have ln of something, and when that happens, the derivative, I don't have to think about it too hard in terms of what to do. I just take, the way that I take the derivative of ln of something is it's 1 over that thing times the derivative of this thing. But the derivative of that, I'm going to have to use the chain rule. So this is really 10x to the 1/2 power. So I could say it's 1/2 times 10x to the negative 1/2 times the derivative of what's inside, which is 10. Now, I could simplify that, and maybe I should. The 2 and the 10 can cancel and give me a 5. And then this is equal to dy over dx is, I have a 5 on the top. This can go on bottom as I have square root of 10x times, this is also on the bottom, square root 10x. So I could write this as 5 over 10x, or if you prefer, dy over dx is equal to 1 over 2x. That's it. Yeah. 69. Okay. 69. Okay, I have ln of 3x plus 1 to the 4th. ln of 3x plus 1 to the 4th. $69. We have ln of 3x plus 9 to the 4th. Oh, I didn't. I guess it's y equals or something. F of x equals, yeah. Okay, so, yeah. Oh, it's 1. Well, I guess sort of. I should probably start with the right problem. Yeah. So 3x plus 1 to the 4th. Okay, so there are 2 ways that I could go about it. I could just take the derivative of it as is because it's just ln of something. But if I want to make it a lot easier on myself, what I would do is I'd say you could take that 4 and move it out of in front of the ln first. So you could say that f of x is also equal to 4 ln of 3x plus 1. This makes the derivative much, much easier. So now you could say that f prime of x is equal to, this is just 4 times the derivative of ln of 3x plus 1 is the 3x plus 1 goes on the bottom. The derivative of the 3x plus 1 goes on the top. That's a 3. And that's it. Now, if you were to do it the other way, like I just want to show you, like if I didn't move that 4 down, what would happen? Well, then I'd get that f prime of x is equal to, well, the 3x plus 1 to the power 4 would go on the bottom. And on top, the derivative of that thing would go on the top. And the derivative is 4 times 3x plus 1 cubed times the derivative of what's inside, which is 3. Correct? But then you see that 3 of these cancel with 3 of these. And you're left with, well, 4. Well, either way, this is 12, right? This is 12 over 3x plus 1. 12 on top, and on bottom, you have 3x plus 1. Yeah. 41? Sure. Let's see. Oh, so somebody asked for 65. Where was 65? Can you move the squared out in front of the ln? You could. Yeah, so because this is really cosine of x quantity squared. And so the squared could move in front of the ln and make it a little bit easier. Somebody asked that on mine. And that is true, yes. So that would make your differentiation a little bit easier. Yeah, that's a good question. Okay, so what did somebody say? I'm sorry. 41?
Yeah.
Okay. 41, we've got y equals 2 to the 3 plus sine x. 2 to the 3 plus sine x, yeah. Okay, so we haven't done one of these yet today, and that is we have an exponential, but the exponential doesn't have base e, it has base 2. So when I take the derivative, dy over dx, I do the exact same thing as if it were an e, and then I have to do a little something at the end to account for the fact that it's not. So if this was e to the 3 plus sine x, the first thing that I do is I just write it again. I just write 2 to the 3 plus sine x. Then if it were an e, I would just then multiply by the derivative of the exponent. So I'll do that now. The derivative of 3 is 0. The derivative of sine of x is cosine of x. And then I have to account for the fact that this is a 2 and not an e. And what you have to do is you just have to multiply by the natural log of the base. And in this case, that's 2. So you do it exact. If this was e to this power, then I would end it here. But since this isn't an e, it's a 2, I have to multiply by ln of 2. And that's the only difference. Yeah.
Can you do 45?
45? Yeah. 45. Okay. So we have a equals 250 times 1.045 to 14. Okay. A equals right. 250, 1.045 to 14, not 2. Okay. So this is really a interesting base problem, because this is like a base not e raised to the 14. So it's the base here, instead of having base 2 raised to some power, I have base 1.045 raised to some weird power. So I'm going to do something very similar. So if I wanted to find the derivative of a with respect to t, the 250 is just a constant, so it just hangs out. And then I need to take the derivative of 1.045 to the 4t. If I have a base raised to an exponent that has variables in it, so I have an exponential, I just rewrite it. So 1.045 to the 4t. And then I need to multiply by the derivative of the exponent, by the chain rule. And the derivative of 4t is just 4. And then I need to account for the fact that the base isn't e. So I need to multiply by the natural log of the base, which in this case is 1.045. And that's it. Does that make sense?
Mhm.
I think the hardest part of this problem probably is just because this is such a weird number, just to say, oh yeah, it's just an exponential. Okay, and then everything kind of falls apart. Yes, sir.
Could you do 35?
35, yes, and I think I'll say that this is the last one because I don't want to do every single one. So 35, we have y equals 2 to the x plus 1 to the pi. 2 to the x plus 1 to the pi. We have y equals 2 to 2 to the x plus 1 raised to the pi. Let's see. 2 to the x plus 1 raised to the pi. Perfect. Okay, so the first thing that I see is I have something raised to the pi. So that's a power rule problem because pi is a constant, right? Pi is not x. It's just a number, 3.1415, whatever. So we've got dy dx is equal to, by the chain rule, I should pull that power out in front, pi times 2x plus 1 to the pi minus 1. So I'm just using the chain rule. So bring down the power times whatever's inside to the pi minus 1. And then I need to multiply by the derivative of what's on the inside. So the inside in this case is 2x plus 1. So I just need to take the derivative of 2x plus 1. Well, the derivative of 2x is 2x times, I've got to account for the fact that the base isn't e, so I have to multiply it by an ln of 2. And then the derivative of 1 is 0, so that's it. Yeah. So it's just a power rule, and then multiply by the derivative of the inside. Okay, that's a good place to stop. Let me talk just for a second about what's coming up, because we're getting close actually to our second exam. So we have a new lesson that homework needs to be completed on. We're doing inverse trig functions. That's due on Wednesday. Then we'll have related rates due on Friday. And then the next week will all just be our exam week. So Monday, I will review for the exam and talk about what to expect on the exam. Wednesday and Friday will both be exam days, kind of like we did last time. Okay, hopefully the Friday won't be canceled by snow, but yeah. So next week will be review day and 2 days of exam. Sound good? Okay, have a great day. I will see everybody on Wednesday.